This video is part of a series of presentations covering the key concepts of multithreading and synchronization. This presentation introduces the concept of synchronization to establish critical sections in multithreaded programs. The presentation covers the principles underlying critical sections, and it also covers the use of mutex and lockguard objects for synchronization. Care must be taken when sharing or operating on shared variables from multiple threads. Imagine a shared variable as an intersection. If multiple threads operate on a shared variable or an intersection, they cause the threads to overwrite or inconsistently update values in the shared variable, resulting in a situation called a race condition. Consider this do-it method that takes a parameter via reference and assume that the main method passes the same reference to the same variable to all of the threads. So all of these threads operate on the same shared variable x, and this update by concurrent threads on the shared variable x causes a race condition, and the value of x after the threads finish is indeterminate. That means the value of x cannot be determined because it was inconsistently updated by multiple threads, which is called a race condition. There are several approaches to developing programs to avoid race conditions. First one is data parallel or synchronization free methods, where each thread operates on its own independent set of memory. Since threads do not share any memory, synchronization is not needed and race conditions do not arise. So for example, in a programming terms, you can have a vector that contains a list of input values, and you can have multiple threads that operate independently on each one of those inputs to generate outputs. And since each thread works on a pre-allocated list of values for inputs and outputs, they do not share any information, and synchronization is not necessary, and race conditions do not occur. On the other hand, many multi-threaded programs will require some form of synchronization. Here, when threads need to update or write to shared memory locations, care must be taken to coordinate the different threads, and this coordinating the different threads is called synchronization. So for example, consider an intersection, which is similar to a shared resource or a variable. Here, synchronization is synonymous to using traffic lights, so that when threads need to go through the intersection, they wait for the traffic lights, and then when the light changes, the other thread goes through. In programming terminology, instead of traffic lights, we have concepts called a semaphore, and a binary semaphore is called a mutex, and these mutexes are used to avoid concurrent updates. So from a programming concept, you would have a mutex, which is like a traffic light, and before a thread does any operation, we have to lock the mutex or lock the intersection so that we have exclusive access to operate on that variable, and then unlock the intersection so that other threads can use the shared variable. Keep in mind the mutex variable is also shared between the different threads, and a thread basically locks and unlocks it temporarily to block other threads from running in the or doing updates to the shared variable. So in this presentation, we're going to do a deeper dive on the concept of critical sections for updating shared resources. That means we're going to look deeper into mutex. We're also going to look at the concept of a critical section created using mutex or lock guards. And then we'll understand the scope of these mutexes to create critical sections. And then we'll look at the performance impacts of working with critical sections. And of course, spend some time to review the 4 important rules for creating these critical sections. So assume that we want to update a shared variable x, and we want multiple threads need to update that shared variable. The only solution to avoid a race condition is to avoid concurrent updates to the shared resource. So that means at any given time, only one thread is allowed to modify that shared variable. Critical section is essentially part of a multi-threaded program where shared values are updated concurrently by multiple threads. So when a critical section happens, a multi-threaded program is coded such that only one thread operates within a critical section. So imagine a critical section as a part of a program. So threads, one thread at a time, go through that line of code to operate or increment the variable x. and threads take turns going through and operating in that critical section. Keep in mind only one thread must be operating in a critical section at any given time. However, before and after the critical section, of course, multiple threads are operating concurrently, and a program can have multiple critical sections one after the other in its operation. Critical section is part of a program where sharing occurs. That means a shared object or data is modified. And there are 4 rules, and these 4 rules are important rules to keep in mind in order to avoid race condition. First, no 2 threads must be operating in the same critical section simultaneously. Keep in mind a program can have different separate critical sections, but given one critical section, only one thread can be operating in that one critical section. When designing programs, we should not make any assumptions about the speed or the number of cores or the speed of the CPU, so on and so forth. We should also try and avoid assumptions about the number of threads as well as much as possible. So any assumptions that you make can potentially cause issues, so we have to try and minimize assumptions that we make in order to ensure we design effective critical sections. A thread that is outside a critical section should not block a thread that is operating inside a critical section. So once a thread is in its critical section, no other thread should be able to block that specific thread. And no thread should have to wait too long to enter a critical section. These days we have gigahertz CPUs, so in such situations, even a millisecond of wait time to enter a critical section can be very expensive for large multi-threaded programs. So critical section should be very short, quick, and thread should be able to get in, lock the critical section, do that operation, and unlock the critical section very quickly. Now let's look at the use of the stud mutex class to create and manage critical sections. So given a thread method that is going to be called from multiple threads, we're going to have a shared mutex object which is essentially going to help us create a critical section. And before we do any operations, we will use the stud mutex object to lock access to that resource or shared variable, and then once we are done with the operation, unlock the shared resource or variable. This locking and unlocking is synonymous to a door, so you can think of the mutex as if it's like a door, a lock to a door. So when there are multiple threads and they want to operate on the shared variable x, the mutex coordinates with the operating system and permits only one thread at a time to acquire the lock. The other threads that are trying to use the mutex will block and wait for their turn to enter and operate in the critical section. So each thread that wants to operate will call the lock, but the operating system will pick some random thread, allow it to lock the critical section and go through it. So it'll pick another thread, lock the critical section, and unlock it. Same way, then it'll pick another thread, it'll lock the critical section, do its operation, and unlock it. So threads take turns to lock and unlock the mutex and operate in the critical section. And it is the programmer's responsibility to ensure the mutex is locked and unlocked appropriately, and it is the programmer's responsibility to identify what shared resources are being updated in a critical section. This is all logic, so the programmer is responsible for ensuring the logic of it is implemented correctly. Keep in mind, unlocking a stud mutex is absolutely important. If you fail to unlock a mutex, your program, other threads will not be able to run, and your program will enter what's known as a deadlock. That means no thread will be able to do or complete its operation after some time. So forgetting to unlock a mutex is a pretty common problem in multi-threaded programs. So for example, notice that here the unlock is inside the if statement. So in some cases, if the x is a small value, then or a large value, sometimes the unlock may not happen. Notice that the lock is happening outside the if statement while the unlock is happening inside the if statement. So this program might work for 1,000,000 iterations. On the 1,000,001st iteration, the program will deadlock. And this kind of issue is very common in complex programs where you have many complicated methods that are being called. So sometimes tracking this lock and unlock operation can be very tricky. And of course, exceptions that may occur. So if there's an exception that occurs, then there's a potential that the lock that was acquired may never be unlocked, and exceptions can in turn, cause a deadlock to occur. So in order to avoid a lot of these issues, we have another API class called the lock guard, which provides a better solution for locking and unlocking mutexes to create critical sections in multi-threaded programs. Let's look at how the lock guard works. So here we are using the guard, we're defining a alias to the lock guard, which is going to work with std mutexes. And notice that when we create a lock object here, the constructor of the lock guard locks the mutex. That means it'll call the mutex lock, which will then block and wait until the operating system allows the thread to acquire the lock so that it can enter the critical section. And then the mutex is automatically unlocked when the scope of the lock guard ends. So here at the end of the thread main method, the mutex is automatically unlocked, and this is exception proof. Even if exceptions occur, you're guaranteed that the mutex will be unlocked. So this approach provides a much better solution to lock and unlock mutexes to create critical sections in a program. So the critical section here essentially spans the scope of the lock guard object. So critical sections can be of different sizes. For example, critical section can just be one line of code. Notice how we have a open curly, close curly scope, nested scope inside thread main. So we can create a one line or a subsection of a method to be a critical section by using that lock guard object. Or an entire body of an if statement can become a critical section. So notice that here the lock is acquired in the body of the if statement, and at the end of the if statement it is automatically unlocked. Critical sections can also be span the scope of a loop. Notice that here the lock is acquired in the body of the for loop. So in each iteration of the for loop, the mutex is locked, and at the end of each iteration the mutex is unlocked. So in this example, the mutex will be locked and unlocked 100 times. Keep in mind here a whole method can be inside part of a critical section, though you should try and avoid it because we want to keep critical section short and fast. But it is possible to have an entire method be a part of a critical section, and all of the methods that it calls here, whatever method thread main calls, it'll all be logically part of a critical section. Of course, if the thread main is going to call other methods that are going to try and lock the same mutex, then it might be better to use what a class called recursive mutex, so that each method can recursively lock and unlock the same mutex. Keep in mind, synchronization using mutexes and locks essentially degrades the overall performance of multi-threaded programs. Keep in mind here, this is because the critical section runs in single-threaded mode, so you can have multiple threads, but in the critical section, only one thread is operating. So critical sections tend to slow down the overall performance of multi-threaded programs. So for example, let's say we have a main method that is going to call create a bunch of threads and that are going to share a variable called x. If you wanted to increment that variable, say 10,000 times, notice that here in the body of the for loop, you're locking and unlocking the mutex, and multiple threads, 10 threads are operating on these locks simultaneously. So threads take turns locking and unlocking. So they are all constantly competing with each other to lock and unlock the mutex. So in this case, notice that the mutex is locked and unlocked by each iteration by 10 different threads. So there are thousands of locks and unlocks that are happening, which can be very time consuming. And in this case, in this specific program, essentially ends up running in single threaded mode because only one thread can ever go through the lock through the critical section at any given time, and most of the time is spent by threads waiting to get into the critical section by locking and unlocking the mutex. So for example, here we could move the lock outside of the for loop. So notice that in the previous section, the lock was inside. Now we're moving the lock outside the for loop. In this case, again, the mutex is locked and unlocked only 10 times, once by each thread. However, again, in this specific example, essentially only one thread runs at a time, because most of the time the threads are running in the only one thread can get a lock at a time, and all of the other threads are going to block and wait to enter the critical section to run that for loop. So even in this case, the performance is not very good. Keep in mind the previous two versions of the program that we saw do follow all of the four rules we looked at. That means no two threads are in the same critical section simultaneously. We have not made any assumption about speed or number of cores as CPUs. No thread outside the critical section is blocking a thread in the critical section. And threads are not waiting too long. I mean, they are waiting for some time, but they're not waiting too long to enter the critical section. However, that does not imply that we have accomplished effective multithreading here, because effective multithreading is still tricky. So it does take some experience to study the program, analyze it, and make sure it is effectively multithreaded. And of course, it is important to test the performance of these programs by timing them or with a profiler to ensure that these programs are effectively multithreaded. So it is absolutely vital that you performance test all of the multithreaded programs to ensure that they are operating effectively with multiple threads. So do not skip the performance testing part. It's absolutely vital. Another way to work with critical sections or to work with mutexes is to use what are known as atomic variables. Here, multi-core CPUs, which are designed to run heavily multi-threaded programs or workloads, synchronization can become a big overhead in large programs. So most modern CPUs support synchronization at the hardware level. And these are accomplished via special CPU instructions. And since these are at the CPU level, they tend to run much faster than software solutions. Keep in mind, it is still a little overhead to use atomic. It's just it is a little bit faster than using a lock guard and a mutex. One drawback or one gotcha with the atomic variables is that you can only use it for primitive data types, that is, those that are directly supported by the CPU. And of course, the primitive data types are like integers, characters, etc. The strict atomic class provides atomic multithreading safe primitive types, so you can use integers, booleans, or doubles. And notice how these atomic variables are created and initialized, where the variable is also initialized in an atomically consistent manner so that the initialization of these variables is also thread safe. Once these variables are defined, you can use them just like any other regular variables. Operations on these atomic variables are all thread safe. That means when you do operations on them, race conditions cannot occur. And in most cases, atomic variables can be used anywhere you use a primitive data type. So wherever you use a primitive data like an int, you can use an atomic int. And you can use them as instance variables. You can use them with containers like vectors and unordered map as well. So let's look at an example of how to work with atomic. So here you would probably include the atomic header. So assume that we want to create a program which is going to operate with 50 threads. So we're going to create 50 threads and have them all operate and wait for them to join. Here we want the threads to increment some kind of a shared variable called num here. We would define this normally as an integer. Instead, we're going to define this as an atomic variable. Notice that here num is atomic. It is still an integer. It operates as if it's an integer, but all of these operations are thread safe. Okay, so here keep in mind that we do not need to use mutexes because num is a atomic variable, and the CPU guarantees that race conditions will not occur when we operate on these shared variables. Again, there are several different operations that are defined on atomic variables. Refer to the API for std atomic to find more details on the different types of operations that are supported on atomic variables. All right, we've started our journey into multithreading and synchronization, so we are pretty deep into this topic. And of course, multithreading and libraries that we've looked at are pretty complex and involved. We will only cover the basics in these presentations, so we're just starting the journeys. And there are several different mutex classes that you can look at, like recursive mutexes, timed mutexes, so on. There are lots of different classes that you can look at with threading. There are several different locking strategies. We looked at stood lock guard. In the newer versions of C++, the preferred class is called scoped lock. Sometimes we can have shared locks, so we can move the locks between threads. There are lots of interesting applications and programming that you can do with multithreading. It's a very involved and complex topic. And of course, you can see some online standard documentation for more details on how to work with threads and all of these atomic variables. Hope you found this presentation useful, and don't forget to check out the other presentations in these series.